Swayam Prabha. Digital India. Educated India.
Well, we have seen this iron carbon diagram, which is based on equilibrium cooling, which means that the cooling rate is so slow that two phases are in equilibrium with respect to each other. So we will see the situation of non-equilibrium cooling, because all heat treatments involve what we call as non-equilibrium cooling, and that is the reason why we will move on to the continuous cooling curve. Now here what we see is that particularly with reference to steel, you have austenite phase which is formed above 723 degrees centigrade, and then if you maintain it at a certain level, it will remain the same, but then you have different possibilities of cooling rates. You have different cooling rates being deployed here. Now this curve, this outside curve, is known as the nose of the temperature time transformation curve. So this axis indicates the temperature, this axis indicates the time, and the transformation. These two curves indicate the extent of transformation that has taken place. So earlier you have a single phase austenite, and then if you were to cool it under equilibrium conditions, it would form, let us say, austenite plus perlite over temperature range as shown earlier. So here for example you would form austenite and perlite. Here you will have cementite and perlite and austenite, cementite and austenite, which austenite will finally get transformed to perlite. On the other hand, here you have austenite with ferrite, and then austenite will finally get transformed to perlite. So you will have a mixture of ferrite and perlite at the end of the day. Here you will have mixture of cementite and perlite. Now this is under equilibrium cooling, very slow rate of cooling. The same thing can be reproduced here also. So you have a very slow rate of cooling, and so that is not the heat treatment we are discussing about. What we are discussing about is some cooling rate which is faster than that, much faster than that. Now we have different possibilities of microstructures, different morphologies of these phases being generated. For example, if you have a cooling rate that is extremely slow, little faster than the equilibrium cooling rate, but very slow cooling rate, then you see that here the transformation starts, here the transformation ends, and what you get at the end is kind of perlite. Here the transformation starts, here transformation ends, cooling rate is much faster than before, but still you get perlite. Now the nature of perlite continues to be different. For example, here it will be little coarse perlite because you are holding it at a high temperature. There is a greater chance of diffusion of atoms, so the thickness of the perlite lamellae will be more because of the greater diffusion distance which is possible at a slow cooling rate. As the cooling rate increases, the diffusion distance decreases, and therefore the lamellae become that much finer. So V3 will be even more fine, and then you have here V4 where you start with the transformation, but you do not finish it. So this is the area, this is the region in which you have austenite plus cementite, or austenite plus austenite plus cementite, and then you have incomplete transformation. Now the question is, does the austenite and cementite remain as they are, or there is any further transformation beyond this? The answer is that there is a transformation where there is another phase called martensite that gets formed. The martensite start is slightly above say 200 degrees centigrade, and then martensite finish is a little below the room temperature at close to minus 100 degrees centigrade. So, our room temperature is somewhere here at, let us say 25-30 degrees centigrade. So, if you have this cooling rate, the transformation is incomplete. So, the incomplete transformation will result in austenite getting transformed into martensite from here on. So, you will have cementite plus martensite combination being progressively developed. Now, here what you will have is austenite plus martensite plus cementite that has been formed already. Okay. But then once you finish, or once you come to the room temperature, you will have martensite plus so called retained austenite at room temperature, because you at room temperature you will not go below the martensite finish. So, there will be again incomplete transformation of austenite to martensite. So, what you will have is martensite plus retained austenite at room temperature, and you will also have the iron carbide that has formed as a result of this beginning of this transformation over here. So, here you will have about 3 phases. You will have iron carbide, you will have martensite and some retained austenite at room temperature. If you were to cool it further down, as we do in case of cryogenic heat treatment, which we will see later, you will find that the entire austenite would have got transformed. So, this retained austenite would have entirely transformed to martensite, and then you will have just martensite and cementite over here. Now, martensite formation is a completely diffusionless transformation. So, what happens is that the atomic movements are extremely small, that they are within the limits of interatomic spacing. So, the movements are that small. So, the transformation of body centered cubic say structure, or a face centered cubic structure of austenite to body centered tetragonal structure of martensite will take place depending upon the percentage of carbon that is present, because high percent of carbon will mean that the body centered tetragonal lattice will have a much greater elongation, meaning the C parameter as shown here will be much higher with increasing percentage of carbon. So, the among the 3 parameters A, B and C, the parameter A, which form the square base of the tetragonal cell, is constant, practically constant. It marginally decreases, but then as carbon increases, there is a significant increase in the height of the tetragonal lattice. So, the C parameter, that is the height of the tetragonal lattice, increases very significantly with an increase in the carbon content. So, we have transformation taking place from FCC austenite to body centered tetragonal martensite without any diffusion taking place, and that is the reason why this transformation is possible when you do not give it any time for diffusion, because as the cooling rate becomes faster and faster, there is decreasing amount of time for diffusion. So, diffusion has 2 things, one is time and temperature. Both the things are denied when you have a large cooling rate, right. You are cooling very fast, so the temperature is diminishing fast, and you do not give enough time for diffusion because that you have reached a low temperature too early for any diffusion to take place. So, this diffusionless transformation takes place at very high cooling rates. Now, if you take these 3 cooling rates, which are slow cooling rates, where the transformation has gone to completion, there even if you cool it further to room temperature, there will be no martensite generated, although this line has gone right up to here, and you might think that it may cut this martensite line after cooling further to room temperature. it is not going to form martensite because there is no austenite that is present. So, you have stable phases in the form of perlite and ferrite or perlite, depending upon the composition, chemical composition of the material. So, you have austenite plus iron carbide which is present here. So, you have complete transformation which taking place up to this point. So, there is no phase that is left that can translate to martensite. So, as long as austenite is absent, there can be no martensite formation. So, austenite is the one that transforms from austenite to martensite. Now, here you are tangential, the cooling rate is just about tangential to this nose. So, here the transformation will just about start, or maybe it will not go through at all because the temperature is decreasing far too rapidly for any kind of transformation to even start or even go to completion. So, here you will have complete austenite, entire austenite getting transformed to martensite, and here you have clearly missed this nose, of the temperature time transformation diagram, and therefore, the cooling rate is too fast. The cooling rate is too fast for any kind of anything other than martensite from getting formed. So, the entire austenite therefore gets transformed to martensite. So, the hardness of the material will depend upon the carbon percentage in this case. If it is a low carbon steel, for example, then you will get nothing in terms of increase in hardness, because the lattice parameter C will be extremely small. As you see here, the lattice parameter will be practical, there will be no increase in lattice parameter C, and so everything will be almost equal. So, it will almost be equal to A. But on the other hand, if the carbon percentage is higher, then the C parameter will increase, so the lattice distortion increases, and due to that the hardness of martensite will be more. So, although the structure may be body centered tetragonal, it with very small amount of carbon, it is practically body centered cubic. So, that is the reason why you get very less hardness of martensite. When carbon percentage is low, you get very high hardness of martensite when the carbon percentage is high. Now, martensite formation involves volume change. So, volume increases when martensite gets formed, because you are converting a face centered cubic cell into a body centered tetragonal, keeping the lattice parameter practically constant. So, the volume increase will be proportional to the increase in the lattice parameter C, right. So, now that is one reason why we observe on many occasions, if the cooling rate is too rapid, then the part cracks, the cracks are formed, because due to volume expansion, tensile stresses get introduced, and we will see why the part cracks when we go to the subsequent slides. Now, you have different properties of these different phases which are obtained. So, you have sorbite, which is here, and then you have a trustite here. So, the different grades of perlite are formed. As you go from top to bottom, you have different grades of perlite. They are lamellar structures, but then yes, in between you can also have what is called as bainite. We will see that a little later. It has got much finer lamellae. So, particularly this particular situation will give you might give you bainite, because it gets into the bainitic region. Just it may give you so called upper bainite. Upper bainite means it is very similar to perlite, but a little coarse. At the bottom you get what is called a fine bainite. We will see these two phases a little later, but I am just introducing them to you at this time. Now, if you get into the details of transformation, you see that the transformation has begun over here, and if you hold the temperature constant for sufficiently long duration of time, then you will complete the transformation by the time you reach here. So, the transformation just starts over here. The transformation percentage continues to increase, and it becomes 100% at this particular temperature. If you hold the temperature constant at this level, the transformation starts here and then goes to completion at this point, right. On the other hand, if you start transformation at a much lower temperature, let us say you hold you move rapidly up to this temperature, missing the nose of the TTT diagram. So, now everything is austenite up to this point and then hold it right up to complete transformation. Then you get transformation starting little late, okay, and then the transformation also completes a little late somewhere there. And so that is the difference it makes when it comes to the different regions in which transformation takes place. So, here the transformation will take much longer, here the transformation will happen in a much shorter period of time. So, that is why when the temperatures are low, the transformations are also a little sluggish, but then the driving force due to temperature not being present, the diffusion distances are very small, and therefore, you will get finer structures here as compared to over there. Now, if you look at the critical cooling rate and the influence of carbon content and grain size on the critical cooling rate, the critical cooling rate is higher with fine grained material and with decreasing manganese. It becomes a little lower, the critical cooling rate becomes a little lower, which is for medium grained material and with 0.4 to 0.5% manganese, and for coarse grained material it is very small. Again, if you look at the shape of the curve, as carbon percentage increases, the critical cooling rate tends to drop over here and then continues to increase. So, if the carbon percentage is of the order of 0.6, 0.8, I mean close to 0.6, then the critical cooling rate will tend to rise beyond this. Now, generally speaking, what happens is that the so called critical cooling rate, which is indicated by this, actually this is the critical cooling rate which is tangential to this temperature time transformation diagram, and it will be lower, okay, it will be much lower if the carbon percentage is higher. So, let us see here. Now, what happens is this TTT diagram moves to the right, and therefore, supposing this moves to the right now, let us say it occupies this position for this curve, and then there is another curve over here. So, this instead of starting the transformation at this curve, let us say transformation starts over here and ends at another curve over here, then these three cooling rates will miss the nose, because now the nose would have got shifted over here, right. So, then what will happen is here the critical cooling rate has come down. So, as the carbon increases, the critical cooling rate therefore comes down. So, the cooling rate that just touches the nose, that just remains tangential to the nose, is much lower than the critical cooling rate when the nose was more to the left. So, when the carbon is relatively low, to get martensite you need a very high cooling rate, much higher cooling rate. The critical cooling rate is also higher. As the nose of the temperature time transformation diagram moves to the right, the critical cooling rate continues to decrease. So, there is a sharp drop. So, so this also indicates a rapid shift to the right as the carbon percentage increases. There is a rapid shift of the temperature time transformation diagram to the right. So, that even at low cooling rates you will get martensite. So, that is the advantage. Now, for example, in case of tool steel, where the carbon percentages are of the order of 1.5% carbon, there you will get martensite even if you leave the material in the air. So, you austenitize it, you heat it to austenitizing temperature, and even if you cool it at a relatively slower rate, then you will get martensite even at a slow cooling rate. So, this means that you can avoid the generation of these stresses and subsequent cracking by cooling at a relatively lower cooling rate, and yet you get martensite. So, you get the hardness, but without any cracking. So, if you cool at a faster rate than that, for example, here you get martensite here, but then you can cool faster than that, this is where you risk cracking more than what you do here. So, as the TTT diagram, temperature time transformation diagram, moves to the right, the cooling rate continues to diminish. Similarly, if there is a fine grained structure, fine grained material, the cooling rate is relatively higher as for a given carbon percentage, the cooling rate is a little higher as compared to when the grains are coarse. Now, we come to some isothermal treatments of steel where again we illustrate how the transformation takes place. So, you see that you start with austenite which is, let us say, 750 degrees centigrade, you have austenite. So, you have the eutectoid temperature, and above that you heat it. So, eutectoid temperature is of the order of 723 and austenite formation. So, you have full austenite at temperature beyond that. So, you have let us say raise it to say 750 degrees centigrade, and then you cool it and hold it at different temperatures. Now, you see that here you have perlite plus austenite generated here. Then so between this and the dotted curve over here, you have the perlite plus austenite. This dotted curve indicates the completion of the reaction. So, you have completion of the perlite formation. Now, if you cool it further down and then hold it at this level, then you get to again you have complete transformation of the you have complete transformation. And so, here what you get is now austenite plus bainite. So, in this region you get austenite plus bainite. Bainite is essentially another phase. We were talking about perlite which forms. So, if you complete the transformation close to the nose or little above that, then you will get perlite. So, that was what we found here. So, the transformation was getting completed over here itself. So, you had austenite plus perlite over here, and so you ended up with the perlite at the end of the transformation. However, here we are a little below the nose, here we are below the nose, and therefore, you get austenite plus another phase called as bainite. It is an independent phase, and therefore, it is a much finer phase, it is much harder phase than perlite. So, you have bainite formation over here, and so if you cool the austenite down without hitting the transformation start curve which is here, then and if you hold it at a relatively lower temperature, then you will get lot of complete transformation of austenite to bainite. Okay. And then here now this is a completely so if you cool it up to this and hold it, you get full bainite transformation. Now, there is another complicated situation where you hold it partly, then there is a part transformation to perlite. So, you see the central dotted line. So, that is the line which corresponds to some partial transformation, certain percentage of perlite has formed from austenite. So, you have a mixture of austenite plus perlite here on this inner dotted line, which lies between the full line and this dotted line, which indicates completion of the transformation. Now, if you cool down rapidly, if you cool down very rapidly to this temperature, okay, then you will have austenite plus perlite here, and then this effectively will go back to this type of situation, because now you have quenched it. There is no change in the phases, because these phases form purely because of diffusion, and by cooling it very rapidly, almost vertically, almost instantaneously, you have not allowed any diffusion to take place. So, the result is that the austenite plus perlite, whatever was available here, is available in the same percentage over here as well. And then you are taking this to the completion of transformation over here. So, what this means is that you have austenite, you have perlite, and this austenite now gets transformed to bainite. So, at the end of the day you have perlite and bainite. Here you had 50% transformation of austenite to perlite. So, that remains intact, but then you transform the remaining austenite, 50% of austenite was transformed to bainite. Had it happened at the top over here itself, it would have completed the transformation would have got completed to perlite. But since you have quenched it, allowing no diffusion to take place, no transformation to perlite to take place beyond 50% of perlite, you have 50% of perlite intact, but then the austenite got transformed to bainite, and at the end of the day therefore you have 50% perlite and 50% bainite. So, the bainite is the transformed outcome of the austenite that was present alongside with perlite. Here you have cooled it down and then you have transformed it through in a normal way, like you have the transformation starts here, it ends there, and then here you have what we call as 100% bainite, because there is nothing else that can remain in present. Now, if you take a very high cooling rate, and you always miss the curve, you miss the transformation curve. So, this is the point where this is the curve describing the initiation of transformation, right. So, you do not want it to transform, you hold it for a while and then you quench it further, you instantaneously cool down to the martensite's finish temperature, then you will have 100% martensite. So, in this cooling curve, so if this had fallen down drastically the way it has been shown, it would have given you 100% martensite, but then that would have been very, very fast. What has been done here is that it has been held here for a certain temperature and then it has been cooled down to martensite. Now, the advantage of holding here above martensite start is that you are not allowing it to form martensite. So, here what we are doing is we are, by holding it at a relatively high temperature for a long period of time, the temperature gets equalized in the entire mass of metal that is being transformed. So, there are no temperature gradients which are left behind. Normally what happens is the surface transforms first, the interior transforms later, and then there are stresses which are generated, because when the interior transforms later there is volume expansion, the surface which has already transformed will tend to contract because temperature is decreasing at the surface, or it has already decreased very rapidly at the surface, and therefore the interior lags behind in terms of temperature profile, and the interior tries to expand, the exterior tries to contract, and then there are tensile stresses set up at the surface and there is cracking. So, by this step of holding this to a temperature of 250 to 300 degrees centigrade, what you are doing is you are achieving homogenization of the temperature without allowing any transformation of austenite to perlite, and then when you cool it rapidly through the martensite start and martensite finish, then you get complete transformation of martensite without risking the consequence of tensile stresses being set up. Yes, tensile stresses will still get set up, but the magnitude will be much smaller as compared to what it would have been if this had gone had fallen further down into the martensite start, martensite finish range. So, between martensite start and martensite finish, you have at different temperatures you have transformations of to different extents of martensite. Here for example, you have martensite finish and you have 100% martensite being formed over here. Similarly, many of these wire ropes which need very high strength, so lifts have got these wire ropes, then the hoists, cranes, these have got they use wire ropes. Now these wire ropes are made from wires of steel, and the microstructure is essentially fully pearlitic in nature. So you have an eutectoid reaction taking place. So what they do is that you have the wires which are drawn from pearlitic steel. Now the microstructure might not be exactly 100% pearlite, so it may contain different phases. So what you do is you austenitize it, you get into a single phase, okay, and then you have what is called as a lead quenching. This is a very important. You don't do water quenching, you do lead quenching. Why? Because 0.8% carbon is a significantly large amount of carbon in the material, and then if you quench these wires in water, they will result in extremely large hardness, extremely poor ductility in the material. Now the ductility in the material is needed for deforming the wires to to be wound over take up payoff reels, take up reels and so on. So some ductility is needed. So lead quenching forms an ideal thing because lead has got a melting point of 328 degrees centigrade. So what happens is that at 328 degrees centigrade, when you quench it in lead, the cooling rate is less for that matter, okay. The cooling rate is less. The strength comes from transformation to what is called as bainite. You don't want martensite, so what you need is bainite formation here, and therefore you have very fine microstructure over here, and that's the reason why holding it to a 328 degrees centigrade is useful. If it is held at high temperatures, you will get coarse pearlite and coarse microstructure, which has got relatively lower strength. So here as you go down, you don't want to form martensite, so it should be above martensite start temperature. So from an industrial point of view, the lead, since it has molten at 328 degrees centigrade, will maintain the temperature at around 328 to 350 degrees centigrade, and here it will take it through to the bainitic stage. So it becomes a continuous process where in one section of the furnace it is austenitized, in the next section of the furnace you have molten lead bath which is maintained at molten lead temperature, slightly higher than the molten lead temperature through which these wires pass. Now the time of residence is extremely important, and if you look at the transformation time, maybe it is a couple of orders of magnitude. So that the furnace will have to be sufficiently long, or the path of these wires will have to be sufficiently circuitous inside the furnace, so that the time of residence is enough for the entire transformation to take place. Now if you compare high melting point materials, lead is ideal because of the fact that its specific heat is 129 joule per kilogram degrees centigrade, which means that the temperature of the lead bath is not going to change in spite of a lot of energy being given away. So you are essentially cooling, so you are taking away the energy from the austenitized wire, and the temperature of the lead bath continues to get maintained at 328 or whatever it has been stipulated. So by virtue of a relatively high specific heat, the temperature, it is easier to maintain the temperature of the lead bath. Well, I have just included another element which is sodium, which has got much higher specific heat, 1228 joule per kilogram degrees Kelvin, and a much lower melting point. But the issue is that sodium is very reactive element, and then it can react, plus maintaining sodium in a molten condition, because sodium being reactive will react with almost anything. It has got very high affinity for moisture, with air and so on. So if you look at the various possibilities, this therefore is not practical, whereas lead is very practical. And in addition to that, in addition to the fact that 328 is a sufficiently large temperature and 129 degrees centigrade, 129 joules per kilogram degrees centigrade is a good amount of specific heat. The latent heat of melting is 23.2 kilojoules per kilogram. So it has got a very high latent heat of melting. So once the lead is molten, it will remain molten for a very long time. I mean, unless, so with a small amount of additional heat, it will continue to remain molten, and the heat comes from the continuously incoming wire. So it can be maintained in a molten condition, and these wires are maintained at that particular temperature for long durations of time. So you have a martensitic grain over here, then you have ferrite and cementite perlitic colonies. So if you hold it in perlite, you will have coarse perlite. Here you will have very fine perlite, and but at this lead bath temperature you have bainite. There are few other heat treatments where you have different kinds of treatments which are combined with the continuous cooling curve. So we know that there are stresses which get generated as we cool very rapidly. So if you hold this after cooling rapidly, you hold for sufficiently long period of time, you get bainite type of structure. So if you hold it for still longer period of time and then cool it very slowly. So earlier what was shown here is cooling very rapidly. So here very rapid cooling was shown, but it is not enough just to cool it rapidly, just get bainite and be done with it. The stresses which are generated during transformation have to be relieved, and so there is some tempering of bainite taking place in the Aus tempering process. So this is one process where the hardness is high and the strength is also very high. Residual stresses are reduced. Here Marr tempering is something where you achieve martensite and then you try to get tempered martensite. So what we do is that we miss the nose of the temperature time transformation curve deliberately, and then we make sure that both at the surface as well as center of the workpiece the nose does not in any way come into play. So you have missed the nose at both surface as well as the center. Having done that, you hold it for a while so that the temperatures at the surface and the center get equalized slightly above the martensitic start. Okay, it gets equalized above the martensitic start, very important. Otherwise, if martensite starts forming, then it will involve volume changes, and the temperature difference between the center and the surface will create problems, which I have already described to you earlier. So now once you have equalized the temperature at the surface and the center by this time, then you let it through the martensite start and martensite finish by cooling it relatively slowly. So the transformation takes place to martensite because the continuous the temperature time transformation diagram is no longer interfering here. You have already missed the nose of this diagram, and therefore there is no transformation taking place by any kind of diffusion. So this transformation to martensite is diffusionless. It now you have come to martensite finish over here. Now again, if you want martensite to be hard, you can leave it at that, but normally what happens is as hardness increases, toughness goes down. So now you want both martensite to be hard as well as tough. So that is why what you do is you heat it again Okay, you heat it again to a temperature which is not well below austenitizing temperature. So you heat it to a temperature where it will form some amount of perlite. So you reduce the amount of carbon in the martensite. So the idea of tempering the martensite is that the carbon should come out of martensite, because as I said, whatever carbon was locked up in the austenite, you know that austenite by virtue of a face centered cubic structure can dissolve lot of carbon, and then you have not allowed it to diffuse out of austenite because you have not let the transformation to take place by rapidly cooling it. So missing the nose of the transformation curve means that no transformation by diffusion has been allowed. So all the alloying elements, meaning the all carbon has got locked up in the austenite, and when it got transformed to body centered tetragonal martensite, you have a very high carbon content in martensite, leading to very high hardness. So if we need toughness as well, then we need to remove some martensite, we need to remove some carbon from the martensite, and that then carbon and the carbon that comes out of this martensite then will form perlite, and so you will get a microstructure of tempered martensite. So basically it's much lower in carbon, it is much lower in hardness, while the hardness due to increased perlite or strength due to increased perlite will go up. So essentially you are increasing the hardness, I mean you are retaining, well it will make some difference to the hardness, it will lower the hardness a little bit, but then your toughness would increase by a significant amount. So in the actual application, what happens is that you have a different shape of the temperature time transformation curve, and this the shape of these curves change depending on the presence or absence of other alloying elements. So it is what has been shown schematically earlier is purely a temperature time transformation diagram when carbon is present, but then there are many other elements which are often added to steel, and therefore that changes in the I mean that changes the shape of the curve. Now you see that in Aus tempering you have this center just missing the nose of the TTT diagram. The surface has missed it by a fair amount. So the cooling has taken place at different rates, surface cooling faster than the center, but then they are held slightly above the martensite start temperature, so that there is complete transformation through the temperature time transformation diagram to a benitic structure. So you do not want it to transform to martensite, so you hold it slightly above the martensite start temperature, let it transform to bainite. So it is lower bainite or fine bainite, and you have 100% fine bainite, which is hard and tough. So it has got very good strength and toughness both. On the other hand, here again center and surface are held at this temperature, then you cool it very slowly, and you temper the martensite as I had I had mentioned earlier, and then you finally finish the process. Then there is a variation of the heat treatment process to include mechanical working also. So it is called as a Marr forming process, where what you do is that you austenitize the material as before, and instead of just holding it at a lower temperature, okay, instead of just holding it at a lower temperature for homogenization of the structure, you deform the material at 900 degrees centigrade or at a high temperature, at an intermediate temperature, then cool it down again very rapidly, and again deform it to deform it at a relatively lower temperature. So what you get here is austenite plus some dislocation density, because now you are working it at a much lower temperature. So austenite is a single phase and it will have some dislocation. So, this process will call as ausforming. So, austenite formation. And 600 degrees centigrade you have two phase, meaning you have partly perlite and austenite. You can have partly perlite and austenite, and then so if you quench it from this itself, then you get quenched martensite, when you will get quenched martensite. But then by deforming austenite at 900 degrees centigrade, what you will get is a high dislocation density and very fine distribution of martensite. So, you have large number of sites on which martensite will start forming, and therefore, you will have a wide distribution. So, you will have finer martensite, uniformly distributed martensite, giving you much better hardness, much better distribution of martensite over the entire microstructure, giving very high toughness, very high properties. So, this is called as Mar forming, where forming is a part of the process itself. So, you have a forming taking place at high temperature and then quenching to martensitic structures. If you quench from 600, some austenite will be remaining, and that retained austenite again will become quenched martensite, and then you will have two phases, perlite and this perlite and martensite. Here you will have entire quenched martensite, which when tempered at 740 degrees centigrade for about 45 minutes will give you what is called as tempered martensite, meaning that part of the carbon of martensite will come out, form carbides. It could form perlite, it could form carbides depending on the alloying elements which are present. So, for instance, if you have lot of alloying elements, then you have M23C6 carbides being formed, where M stands for different kinds of metallic constituents. So, in Mar forming you introduce the forming process. So, instead of holding it here, you deform it. So, now this deformation can be given at a much higher temperature, and then you can quench it to the martensitic structure. So, as you see here, holding it here, you work it at a much higher temperature and then quench it to a martensitic structure. Now, we have another process called as annealing. We have said that we hold the temperature slightly above the 723 degrees centigrade, where it is again typically single phase. I mean the temperature of 723 degrees centigrade is the austenitizing temperature for perlitic material. But then the temperatures where full austenite is formed will change depending on the chemical composition on either side of the eutectoid point. So, you have holding temperature slightly above 723 degrees centigrade, and you slowly cool the material, where internal stresses get relieved primarily by decrease in the yield stress of the material. So, the yield stress of the material reduces below the magnitude of residual stresses being present in the material, and so the very local plastic deformation takes place, and there is nothing else happening. Well, partial recrystallization may occur because different grains are at different stress levels. So, you may have partial recrystallization taking place, but if at all it takes place, I mean we do not expect partial recrystallization at this temperature, but yes, we allow for a very small amount of this event to take place. And so, ferrite in hypoeutectoid steel and cementite, so none of the microstructural elements go into solution. So, you do not get an austenitic phase as such. As I said, when you talk about hypoeutectoid steel or hypereutectoid steel, then the temperature for austenitization is much higher than 723 degrees centigrade. So, the 723 degrees centigrade is the temperature at which you might just about start forming or start converting perlite into austenite, but that does not happen very very rapidly because the temperature is too low for that. And so the microstructure remains intact, though there is no change in the microstructure. So all that happens is the relief of stresses, internal stresses are relieved, which means that the yield point of the material being a little lower results in small amount of plastic deformation and nothing else. So you have the dislocation density is also maintained at the same level. So if you have worked the material a priori, if you have, let us say, worked the material in the two phase region for example, then if you do the stress relief annealing, hold it at 723 degrees centigrade for a certain period of time and then cool it and cool it very slowly, then the microstructure will not change, the dislocation density will also not change, but what will happen is the internal stresses which are present will be relieved because of local plastic deformation taking place due to the temperature bringing down the yield strength of the material to a level below the internal stress levels. So that is why it is applied to eutectoid and hypereutectoid steels, and if you heat eutectoid and hypereutectoid steel well above this temperature, then it can cause complete recrystallization. So completeness of recrystallization would occur only at much higher temperatures. Now if you look at the mechanical properties after annealing, you have let us say the ductility increasing and the strength, the yield strength of the material decreasing. As the carbon increases, as the percentage of carbon increases, the yield strength is of course going to increase. So the yield strength will increase with percentage of carbon, but then after annealing the material will become softer than what it was before annealing. So now if you look at the internal stress relief, the yield strength will remain the same because internal stresses have been relieved, and the stress will otherwise remain the same at the end of the annealing process, because you have not reduced the strength of the material, all you have done is you have done stress relief annealing. So the yield strength of the material will still go higher, okay, with the increase in the carbon percentage. Now if you look at the transformation diagram, we have already seen this. So if you look at the steel to obtain perlite, then when the workpiece size is small, then the center and the surface are practically at the same temperature. So both of them, both the surface and inside will undergo a very similar transformation. Now if you look at the possibility of grain growth during recrystallization or during any kind of heat treatment, then you have a certain temperature beyond which coarse grains start forming. So there is certain incubation period for the grain size to increase. So here you have let us say you start with fine grains. Normally what happens is, if you start with fine grains, the grains tend to remain finer, but if you start with a coarse grain size, then you have coarse the grain growth takes place. So here you have fine grains. Now initial period there is a non-uniform grain growth, and then there is uniform grain growth. So you have medium sized grains and coarse grains and fine grains, all three having growing to different extent, but then beyond the time the period of uniform grain growth takes place. So then the finer grains tend to grow more rapidly as compared to the coarse grains. So here so if you have started with a fine grain structure, it will remain fine grain structure up to this, but then later on it can coarsen very rapidly. So if you look at the this curve, as the temperature increases, as the temperature increases, the grain growth increases very rapidly, and if the carbon percentage is increasing, if the carbon percentage is large, then the grain size will also tend to increase very rapidly. That is what is shown over here. So, if you look at the grain growth of fine and coarse grained steels, if the austenite, so control of grain size at solutionized level, meaning at austenite level, is very important, because it is very difficult to get a fine grain size after you have cooled down the material. So, at austenite level itself, if one is able to control the grain size, then you can have the desired grain size at relatively lower temperatures after the completion of annealing. So, you have inherently coarse grained steel, so the grain size does not remain any finer, but if you have successfully reduced the grain size at the austenite level itself, then you have these fine grained steels which would go up to a certain temperature without coarsening very rapidly, but then after that the coarsening will be far more rapid. So, here what is happening is the grain boundary area is being reduced. So, the grain boundary area, being a region of high energy, gets reduced very rapidly beyond a certain temperature. So, the stability in terms of energy is achieved by reducing the grain boundary area, meaning by grain coarsening. So, this is why fine grained material which has got large grain boundary area has got a lot of energy in terms of grain boundary energy, but that is rapidly reduced as grain growth takes place rapidly beyond a certain temperature. So, we have discussed this. Now, we come to a few other hardening treatments, because we need to harden the material, and so we need to take it to a high temperature. So, the typical heating temperatures for hardening of the material are given here. So, you heat it to the austenitizing temperature. Here you heat it to austenite plus iron carbide, because here there is no need to austenitize it fully, because iron carbide itself is a very hard phase. So, when austenite gets transformed to martensite, you have iron carbide and martensite. If you have if you are able to transform it at a very slow rate, then you will get iron carbide plus pearlite, but iron carbide itself is a very hard phase. So, now if you look at the heating schedules for different kinds of steels, meaning when you are doing the heat treatment, you need to heat the material to high temperatures. We have been trying to understand the fundamental that the temperature gradient across the geometry of the product can be deleterious. So, if you have a high alloy steel, if you have large workpieces, that too of high alloy steel, then the heating rate has to be kept at extremely slow rate. I mean, the heating has to be has to follow a very over a large period of time. So, that is why you have a furnace temperature which is much higher initially, and then you see that the surface temperature and the interior temperature are vastly different. The core temperature rises very slowly as compared to the surface. The surface will tend to be in tune with the temperature of the furnace, and so the delta T is the temperature difference between the core and the surface. So, this delta T is will rise up to a certain period of time, and then it will go down. So, the delta temperature, the difference in temperature will increase first, because the surface is getting heated rapidly, and then as the heat diffuses to the central portion, then the temperature differential will diminish. So, this requires a very long heat treatment or long heating cycle. So, the heating cycle is very long for high alloy steels or large workpieces. Now, high alloy steels have another issue, that is of lower heat thermal conductivity. So, lower thermal conductivity, in addition to the fact that the workpiece could be large, enhances the temperature difference between the core and the surface. So, that is why for both, if two conditions of workpiece being large and the material being highly alloyed, the heating cycle has to be extremely gentle. If it is very rapid, then there is a risk of cracking at the surface, because the surface would expand much faster than the interior, and significant tensile stresses would get set up during the course of heating. If we take small size parts, so the cross section is relatively small, so the difference in the temperature at the core and the surface does not remain does not get sustained for too long a time. So, here for example, you have to reheat the furnace very slowly to the heat treatment temperature. Here the furnace can be maintained at the heat, so there is a constant temperature that is maintained. The part is charged at that temperature, and then the part rapidly acquires that temperature. So, the heating rate here is much greater than the heating rate over here. So, here the temperature itself, temperature of the furnace itself is relatively smaller. So, the temperature rises over a significant period of time in the furnace, whereas here the temperature has already risen to the desired temperature, and when the part is charged, it acquires that temperature very rapidly. And because the cross section is relatively small, you do not have any issue on equalization of the temperature. So, for a very short while the temperature difference persists, and the equalization of the temperature occurs much quicker. So, delta T diminishes over a much larger time. In case of high alloy steels and large workpieces, it will diminish more rapidly. The delta T will diminish more rapidly with smaller workpieces and better conducting parts. So, wherever you have higher thermal conductivity, either because the material itself is like aluminum or copper, or because the alloy content of steel is relatively low, the conductivity will be that much higher, and therefore, these two will get homogenized much quicker. So, for low carbon steels, you can have what is called a forced heating. So, which means that you heat the furnace to a much higher temperature than what is necessary. Okay, you heat the furnace to a much higher temperature. This is more aggressive kind of heating, right, because now the temperature will rise very rapidly. So, what you are doing by heating it aggressively is that you are forced heating, meaning the temperature of the furnace is taken to a much higher temperature than what is necessary. So, the temperature differential between the workpiece and the furnace is initially very high. So, the heating rate of the workpiece is extremely high over here. So, if you have low carbon steels where thermal conductivity is very high, or you have extremely small workpieces, then under both these conditions you will get very rapid heating possible without any adverse consequences. The temperature of the furnace can then be brought down to the desired temperature level over a period of time as the parts get heated, and so the heat treatment cycle is or heating cycle is much quicker, because the temperature differential lasts for a very short period of time, the shortest period of time among all three between the core and the surface. So, the temperature heating is going to last for a very short period of time. But although although in heat treatment schedules fast heating is possible for many materials, people do not so wherever fast heating rate is possible, you need to adopt that to the extent possible because of the expenditure on heat treatment, because heat treatment is an extremely costly process. So, lot of energy is spent on heat treatment, and therefore, it is important to preheat the workpieces wherever possible. So, you preheat the workpiece initially and then bring it into the furnace, so that the furnace energy that is needed is much less. Plus, having preheated the material earlier, there is better homogenization of the temperature between the surface and the interior. So, when you adopt a faster heating rate, then the temperature differential will can be reduced by that much if the preheating of the workpiece is carried out. So, waste heat can often be used for preheating. The waste heat from the furnace can be used for preheating of the material and holding it there for a long period of time, and then getting it into the furnace for better utilization of the heat, as well as for shortening the heat treatment schedule or heating schedule in particular. So, even with high alloy steels, one can shorten this heating time by preheating. Now, we have different types of furnaces. For example, I mean, we are just talking about temperature, and how it is achieved is something we really did not consider. So, if you look at two different types of furnace where fuel is burned, in box furnaces you burn either gas or oil. So, these have different heating rates, and comparatively salt bath where you have molten salts. Now, these salts have got very high specific heat. So, once heated to their melting temperature, they can be held at that temperature without any difficulty for long durations of time. So, the temperature control with salt baths is much better than the box or that is box furnaces, be it gas fired or oil fired furnaces. So, in case of salt baths, the heating time and the holding time is much lesser. That is because molten salts are more efficient in transferring heat to the workpiece, in retaining heat in the bath, whereas these require the gas or oil fired furnaces require a much greater heating time for a given thickness of the part or given cross section of the part. So, the holding time is also more, the heating time is more. Now, you use what is called as convective heating in both the cases, but in case of salt baths, the body of the salt, amount of salt, that molten salt is far too high as compared to the volume of the workpiece, and therefore you get very rapid heating and retention of the heat for the duration of time it is in, and so the time needed to equalize the temperatures at the center and the surface are much lower. So, as the thickness goes on increasing, the holding time also increases, which is well understood. The heating time also increases because you do not want the surface to get heated very rapidly. After all, in either case, the heat is going to progress from surface inwards. So, the heating time has to increase, and particularly when alloy steels are present, when your thermal conductivity is lower because of alloying elements, then the heating time should be increased by 25 to 50%. So, the heating time has to go to say 240 minutes when the part is 200 millimeter thick or 200 millimeter diameter or something thereabouts. So, what it means is that we need to therefore go a little slower, go more gently in heating the parts which have got a greater cross sections. So, holding time will also proportionally increase to by 50%. So, the entire cycle will therefore increase. So, you have different salt bath compositions with different melting points. So, depending on the heat treatment temperature that you desire, you can have the salt composition. You add different percentages of salts, as you see a mixture of salts which have a specific melting point. Now, similar to a single melting point of the eutectics, if we consider many of these salt combinations, they will have a single melting point at which they can be deployed. So, if the salt mixture has got a single melting point, then the temperature control becomes that much easier. Now, there are certain disadvantages with the with each of the salt baths beyond a certain beyond its domain of application. The risk is that 100% NaCl, for example, you have let us say 850 degrees centigrade to 1100 degrees centigrade as the temperature range, but then there is a risk that it will decarburize the steel, and the same is the risk with many other materials like salts like barium chloride. So, unless that the temperature of the duration of exposure is not too large, if the duration of exposure is not too large, one should not use a particularly high carbon steel, NaCl salt bath with for high carbon steel. So, there are many compositions which decarburize at different temperatures. Below that this temperature it is okay, but beyond a certain temperature, so basically we need to be aware that decarburization takes place. So, we will get into the details of on how oxidation and decarburization of the steel takes place, what are the causes, and how one can avoid these things, how one can deal with these things during heat treatment is something we will see in the subsequent lectures. Thank you.